Where is the universe expanding to? We've come to the new year, and there are just a few days left until we enter 2026, and we continue our explorations. Right now, the universe is growing so fast that every second the distance between distant galaxies extends by thousands of kilometers. But here's the part that raises curiosity. The universe is not expanding toward anywhere. That is, there's no giant warehouse, no boundary line, no larger container that needs to be filled. Now we're going to embark on a journey into science's most mind-boggling concept. We'll discover how space creates itself from nothing. We'll see the invisible force that tears reality apart, and we'll understand that asking where the universe is expanding to is like asking what's north of the North Pole. For this cosmic journey, please like and subscribe. Let's continue our explorations together. If you're ready, we're starting. Where the balloon analogy goes wrong. Now let's imagine a balloon inflating in your living room. As you blow air into it, the rubber expands outward, pushing against the surrounding air. The balloon grows because there's space for it to grow into. Your living room provides this space. This makes perfect sense to us. This is how expansion works in our daily life. But the universe doesn't conform to this logic. When cosmologists tell you the universe is expanding, your brain immediately wants to imagine that balloon. You think that space is extending toward somewhere, toward a cosmic room, toward a tremendous void waiting to be filled. You assume there must be a boundary where our universe ends and something else begins. This thought feels natural. It seems appropriate. This is exactly where physics breaks these assumptions of yours. The universe is not like that balloon. When space expands, it doesn't push toward somewhere. There's no cosmic living room. There's no container. There's no outside. The universe creates the very concept of space as it grows. Think of it like this. Imagine trying to draw a circle larger than your paper, but instead of getting a bigger paper, the paper grows on its own to accommodate your circle. This seems impossible because in our world, everything expands towards something else. Plants grow toward the air. Cities spread toward the countryside. Ice expands over water. There's always somewhere for the expansion to go. There's always a boundary between the expanding thing and the place it's trying to expand into. But what if you were both the paper and the drawing? Hubble's surprising discovery. Scientists discovered this mind-boggling reality by observing distant galaxies. Edwin Hubble noticed that galaxies farther from us were moving away faster than nearby ones. At first, this makes you think we're sitting at the center of a cosmic explosion, as if everything is flying toward empty space while we sit in the middle. The truth seems much stranger. Space itself is stretching. Galaxies aren't moving through space. The space between them is growing. Imagine dots on a balloon that's starting to deflate, but in reverse. As the balloon inflates, the dots move away from each other without moving on the surface. The surface itself is expanding. Each dot sees all other dots moving away. No dot is special, no dot is at the center. Now, replace that balloon surface with the three-dimensional space you live in. The universe isn't expanding towards somewhere because there's nowhere for it to expand to. It creates the stage on which expansion can occur. This breaks our intuitions so completely that reliable scientists struggled with it for decades. Albert Einstein himself initially rejected this idea. Yet this impossible expansion is happening right now, happening much faster than you can imagine. The torture of light. So how can we be sure this strange process is real? The answer is it lies in observing the light that's tortured by expanding space. When a distant galaxy sends a beam of light toward Earth, that light begins its journey with a specific wavelength: blue light, red light, infrared. Each wavelength carries a signature, like a cosmic fingerprint. But as light travels through expanding space, something extraordinary happens. The space that light passes through grows during its journey. Imagine walking on a moving walkway that's slowly extending. Your steps remain the same size, but the ground beneath you constantly extends. By the time you reach the end, you've traveled much farther than your steps should have taken you. Light experiences something similar, but instead of traveling farther, its wavelength extends. Blue light from a distant galaxy reaches our telescopes as red light, not because the galaxy is moving away like how a speeding ambulance changes its siren sound. The light becomes redder because space itself expanded during the light's billion-year journey. As the cosmic fabric grew, each light wave became longer. This process, called cosmological redshift, proves to us that space grows independently of the objects within it. Here's the number that will rewire your brain. Light from the most distant observable galaxies has been stretched to nearly 40 times its original wavelength. The space that light traveled through expanded so much that what started as intense ultraviolet radiation now reaches us as faint infrared heat. Wavelengths 40 times longer mean the universe expanded 40 times during the light's journey. Think about it like this. The galaxy that sent you this ancient light appears tiny and faint in our most powerful telescopes. But when that light first left the galaxy, the universe was 40 times smaller than it is today. That galaxy was much closer to where our Milky Way would eventually form. Space didn't just grow a little, it underwent massive, relentless, unexpected expansion. Expansion is everywhere. But here's what makes this an even more mind-confusing problem. This stretching isn't happening somewhere else. It's happening everywhere. Right now, the space in this room is trying to expand. The space between your eyes and this screen wants to be bigger, it seems. The only reason you don't notice this expansion is that the electromagnetic forces between atoms are much stronger than the expansion rate. Only across tremendous cosmic distances does this expansion become noticeable. In the space between galaxies, there are no atomic forces holding it together, so it expands freely and carries these galaxies along, like raisins in rising bread dough. The raisins don't move through the dough expands and separates them. This is why the question, what and where is the universe expanding to, completely collapses. You're asking what the dough is expanding into, but you're part of the dough. Cosmic prison. However, if space is stretching everywhere, how far can we actually see? We live inside the ultimate cosmic prison, with walls made of time itself. Every night when you go outside and look at the stars, you feel like you're seeing the universe, the whole thing, all of reality stretched out above you in that dark sky. But here's the truth that will reshape your thinking about existence. You're seeing less than 4% of what's actually there. You're trapped inside an invisible sphere. This sphere has a radius of approximately 46 billion light-years. Beyond this boundary, there's more universe, billions more galaxies, trillions more stars, perhaps even other versions of you reading these words right now. But you will never see any of them. Not with any telescope humanity could build, not with any technology that could exist. The trap isn't made of walls or barriers. It's made of the finite speed of light and the finite age of the universe. Light needs time to travel. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star system, Alpha Centauri, you see it as it was 4 years ago. Look at the Andromeda galaxy and you're looking 2.5 million years into the past. The farther you look into space, the deeper you look into history. Here's where the trap closes around you. The universe is 13.8 billion years old. This means the oldest light that could possibly reach you has been traveling for 13.8 billion years. Any galaxy farther than 13.8 billion light years away might not exist from your perspective. Its light hasn't had enough time to reach you yet. But wait, the trap becomes even more restrictive. Remember that space has been expanding all this time. That distant galaxy was much closer to us when it emitted the light we see today. By the time its ancient light reaches our telescopes, expansion has carried that galaxy far beyond the 13.8 billion light-year mark. Today, that galaxy sits approximately 46 billion light-years away from us. This creates your cosmic prison cell. Everything beyond 46 billion light-years from Earth exists in what scientists call the unobservable universe. You cannot see it, you cannot detect it, you cannot prove it exists. Yet logic and mathematics tell us it must be there. Think of yourself standing in a dense fog that limits your vision to 100 meters in every direction. You can see a circle of ground around you, but you know the world continues beyond that fog. The observable universe is your fog-limited circle, while the actual universe extends infinitely in all directions. Here's the number that should both frighten and amaze you. If the universe is infinite, your observable bubble contains 0% of what actually exists. 0%. Cosmic microwaves background. So what's beyond our cosmic prison walls? The oldest light in the universe is currently hurtling toward you at 600 million miles per hour, and it carries a message from the moment reality began. This light has been traveling longer than Earth has existed, longer than our solar system formed, longer than our galaxy took its current shape. This light began its journey when the universe was only 380,000 years old. Back then, the cosmos was a seething plasma so hot that atoms couldn't even form. We call this the cosmic microwave background, and it's everywhere. Turn on an old television between channels, and about 1% of that static is coming from this primordial light. You're literally seeing the afterglow of creation flickering on your screen. This radiation fills every cubic centimeter of space. It comes from every direction at once. It's the oldest thing the human eye can detect. But here's what makes this discovery so profound. This light represents the boundary of everything we can observe. Before that moment, 380,000 years after the Big Bang, the universe was opaque. Imagine trying to see through the surface of the sun. The early universe was like that everywhere, a thick plasma fog blocking all light. No photon could travel more than a few centimeters before colliding with charged particles and being absorbed. Then, something miraculous happened. The expanding universe cooled enough for protons and electrons to combine into the first hydrogen atoms. Suddenly, the cosmic fog lifted. The universe became transparent. Light could finally travel freely through space. The first photons that escaped this cosmic clearing are the ones reaching your eyes today as the microwave background. This moment, called recombination, created the ultimate horizon. You can never see beyond it. Any event that happened in those first 380,000 years remains forever hidden. It's like trying to see through a brick wall surrounding the entire early universe. The cosmic microwave background is that wall and represents the absolute limit of observation. Beyond the horizon. Here's the mind-bending part. This horizon moves every second. Light that has been traveling for 13.8 billion years plus 1 second reaches us. The observable universe grows by 1 light second every second. This means approximately 186,000 miles of new space comes into view. Every day, we can see about 16 billion miles farther into the cosmos. But expansion complicates this growth. While our observable horizon expands, the actual distance to the source of that ancient light continues to increase due to cosmic expansion. The galaxy that emitted a photon 13 billion years ago now sits approximately 30 billion light-years away from us. We see where it was, not where it is. This creates a strange situation. We're constantly seeing new regions of space, but the sources of that light are constantly moving away from us. It's like watching a movie of someone walking away from you while the screen gets bigger.
The cosmic microwave background shows us the universe when it was smoother than a perfectly polished mirror, with only temperature differences of a few millionths of a degree. Those microscopic temperature differences would eventually become everything. What's beyond the horizon? Beyond the boundary of everything you can see, there's more of exactly what you can see. This sounds boring, but is actually the most disturbing possibility in cosmology. If you could somehow teleport 47 billion light-years away, beyond your observable boundary, you'd find yourself in a region surprisingly similar to here. More galaxies, more stars, more planets, probably more life. The universe appears homogeneous on the largest scales. Homogeneous means uniform, the same everywhere, like a perfectly mixed cake batter where every spoonful contains the same ingredients in the same proportions. Our observations of the cosmic microwave background show that the universe has this property. The small temperature variations we detect are smooth and consistent across the entire sky. This smoothness tells us something profound about what's beyond our view. If the observable universe contains roughly 2 trillion galaxies, then a region of identical size just beyond our horizon should also contain roughly 2 trillion galaxies, and another region beyond that should contain another 2 trillion. The pattern continues forever, or at least much farther than we can comprehend. Disturbing consequences of an infinite universe. But here's where this becomes psychologically disturbing. If space is truly infinite and homogeneous, then every possible arrangement of matter within any volume must repeat somewhere. This isn't mystical thinking, it's a mathematical necessity. With infinite space and finite ways to arrange a finite number of particles, repetition becomes inevitable. Imagine you have a deck of cards and you shuffle it infinitely many times. Eventually, you must get the same arrangement twice. The universe works similarly, but with atoms instead of cards. This means there are other versions of you reading these words right now, not metaphorically, literally, in regions of space so distant that their light will never reach us. Quantum mechanics has arranged matter in every possible way, including arrangements identical to your current configuration. Mathematics suggests these copies exist at distances of roughly 10 to the 115 meters away. This is such a large number that if you wrote it out, the line of digits would spread across more space than exists in our observable universe. Yet, if space is infinite, these distances are still finite. Somewhere, another you is having this same realization about yet another you even farther away. Dark energy. But wait, this assumes the universe beyond our horizon looks like ours. What if it doesn't? Recent observations provide hints that our local region might be unusual. We seem to exist in a cosmic void, a region with below-average galaxy density. If this is true, traveling beyond our observable horizon might reveal denser regions of space filled with more galaxies, more black holes, more activity, or it might reveal nearly empty regions. Some theoretical models suggest that cosmic inflation, the rapid expansion in the universe's first fraction of a second, could have created regions with vastly different properties, different physical constants, different particle types, entirely different laws of physics. These pocket universes might exist just beyond what we can observe and operate under rules that would render our physics textbooks useless. How does an infinite universe expand? However, hiding beneath all these speculations is an even more fundamental question. What if the universe isn't infinite at all? An expanding infinite universe presents one of the most beautiful paradoxes in physics. How do you make infinity bigger? Mathematics tells us this should be impossible. Infinity plus anything still equals infinity. Infinity times 2 still equals infinity. You cannot add to something that already contains everything. Yet, our observations clearly show that space is expanding everywhere.
Even if the universe extends infinitely in all directions, the solution comes from understanding what expansion really means. When we say the universe is expanding, we don't mean it's growing bigger in the sense of becoming more infinite. We mean the scale of space itself is increasing. Think of it like this. Imagine an infinite piece of graph paper where each square is 1 inch wide. Now imagine stretching that paper so each square becomes 2 inches wide. The paper is still infinite. It still has infinitely many squares, but the distance between any two marked points has doubled. This is exactly what happens during cosmic expansion. The universe doesn't become more infinite. The scale factor of space increases, causing all distances to grow proportionally. A galaxy that's 100 million light-years away today was 50 million light-years away when the universe was half its current size. But this creates a disturbing consequence. If the universe is infinite now, it was also infinite at the moment of the Big Bang. This means a Big Bang wasn't an explosion of matter and energy from a single point into empty space. It was the simultaneous expansion of infinite space filled with infinite energy everywhere. Grasp this. The Big Bang happened everywhere at once across infinite space. There was no center, no edge, no outside, just infinite space that suddenly began expanding and cooling. Every point in the universe can claim to be the center of expansion because expansion looks the same from every location. Quantum vacuum and the creation of space. The universe is producing new space from pure nothingness at a rate of approximately 10 to the 78 cubic meters per second. This is a number so large that if you tried to count that high, one number per second, you'd need more time than the universe has existed, multiplied by itself billions of times. All this new space emerges from the quantum vacuum. The quantum vacuum isn't the empty void you might imagine. It's a seething foam of virtual particles popping into existence and annihilating each other in timeframes shorter than the smallest measurable instant. This process, called quantum fluctuation, fills every point in space with energy. Even in the most perfect vacuum, this quantum activity continues. Here's the mind-bending part. This vacuum energy has gravitational effects, but unlike matter, which pulls things together, vacuum energy creates repulsive gravity. It pushes space apart. The more space you have, the more vacuum energy you get. The more vacuum energy you get, the more space expands. The more space expands, the more room there is for new vacuum energy. This creates a runaway process called inflation. During the universe's first tiny fraction of a second, this process ran wild. Space expanded faster than light could travel. Not because anything moved faster than light, but because space itself grew faster than light could cross it. In less than a trillionth of a trillionth of a trillionth of a second, a region smaller than a proton expanded to roughly the size of a basketball. This sounds like science fiction, but quantum mechanics demands it. The uncertainty principle tells us that energy can be borrowed from the vacuum, provided it's paid back quickly enough. During inflation, the universe borrowed enormous amounts of energy to create new space, then used the expansion itself to pay back the debt. It's like taking out a loan to buy a money printing machine, then using the printed money to pay off the loan. The process worked so well that it overshot. Inflation should have stopped after creating enough space to solve certain cosmological problems. Instead, it continued, creating far more space than necessary. Our entire observable universe represents just a tiny patch of the much larger inflated region. Think of inflating a balloon to the size of Earth, then examining just a patch the size of a pinhead. That pinhead is our observable universe compared to the region inflation created. Dark energy and our future. But here's what makes this truly strange. The process continues today. Current expansion isn't inflation, but operates on similar principles. Dark energy, which makes up approximately 68% of everything, behaves exactly like vacuum energy. It fills space uniformly and creates repulsive gravity that accelerates expansion. As the universe grows, more dark energy appears to fill the new space. This violates every intuition you have about energy conservation. Energy cannot be created or destroyed, yet expansion seems to continuously create new dark energy. The resolution lies in understanding that gravitational potential energy is negative. As space expands, matter spreads out more, reducing gravitational binding energy. This negative energy balances the positive energy of newly created dark energy. The universe maintains perfect energy balance while creating infinite new space. This process will continue forever, or at least for longer than human minds can comprehend. Each moment brings new space, new dark energy, and accelerated expansion. The universe grows not because it needs to expand into somewhere, but because expansion creates its own space. Big Rip, the Great Tearing. In approximately 22 billion years, dark energy might become so powerful that it could tear apart every atom in the universe, shredding reality itself down to its fundamental components. This catastrophic end, called the Big Rip, makes heat death look gentle. Instead of slowly fading away over trillions of years, the universe would destroy itself in a final spasm of expansion that overwhelms every force in nature. The destruction follows a terrifying timeline. About 1 billion years before the Big Rip, dark energy becomes strong enough to overcome gravity on galactic scales. Galaxy clusters dissolve as space expands too rapidly to hold them together. 200 million years before, expansion tears apart individual galaxies. Stars are ripped from their galactic homes and scattered into the growing void. The Milky Way dissolves. Andromeda disintegrates. 30 minutes before, expansion overcomes the gravitational binding of solar systems. Earth breaks away from the sun. The moon drifts away from Earth. Every planet in every solar system throughout the universe suddenly finds itself alone in expanding space. 90 seconds before, expansion becomes strong enough to overcome molecular bonds. Atmospheric gases surrounding every planet disperse into space. Oceans boil, not from heat, but because the space between water molecules expands faster than intermolecular forces can maintain liquid cohesion. 10 to the minus 12 seconds before, atomic nuclei disintegrate. The strong nuclear force holding protons and neutrons together finally succumbs to the relentless stretching of space. Every atomic nucleus in the universe spontaneously breaks apart into protons and neutrons. At the moment of the Big Rip, even space and time themselves might disintegrate. Some models suggest that space can only stretch so far before the concept of distance breaks down. The metric that defines how to measure lengths and time intervals becomes infinite. Causality fails. The universe doesn't just end, it becomes physically meaningless. Einstein's greatest mistake. Albert Einstein added a term to his general relativity equations that he later called his greatest mistake. But this term turned out to be necessary for understanding the accelerating expansion we observe today. In 1917, Einstein faced a problem with his newly completed general relativity theory. The equations predicted that the universe must either expand or contract. They didn't allow for a static, unchanging cosmos. But everyone knew the universe was static and eternal. At least that's what astronomers of the time believed. Einstein trusted the observational evidence and modified his equations. He added what he called the cosmological constant, represented by the Greek letter lambda. This term acted like a repulsive force that could exactly balance gravity's attractive pull, allowing the universe to remain static despite containing matter. The cosmological constant represented the energy of empty space itself. Einstein envisioned this space energy as a fundamental property of the vacuum, creating a gentle outward push that prevented gravitational collapse. For more than a decade, this seemed like a reasonable solution. Then, Edwin Hubble discovered that distant galaxies were moving away from us. The universe wasn't static after all, it was expanding, just as Einstein's original equations had predicted. Einstein quickly abandoned the cosmological constant and characterized it as his greatest mistake. If he had trusted his original equations instead of the flawed observations, he would have been predicting cosmic expansion decades before Hubble discovered it. But the story doesn't end there. In 1998, astronomers discovered that cosmic expansion is accelerating. Something is pushing space apart with increasing strength, exactly what Einstein's cosmological constant was designed to do. Einstein's mistake turned out to be necessary for our understanding of the universe. Current observations suggest the cosmological constant provides the best fit to the data. If this interpretation is correct, Einstein's intuition about the energy of empty space was quite prescient. Each cubic centimeter of empty space contains approximately 10 to the minus 10 joules of dark energy. This seems insignificant, but when multiplied by the enormous volume of the observable universe, it reaches more energy than all matter and radiation combined. Einstein's supposedly unnecessary term dominates cosmic evolution. Hubble's revolutionary discovery. Edwin Hubble spent night after night in 1929 measuring the distances and velocities of distant galaxies and accidentally discovered that the entire universe was flying apart. Working at Mount Wilson Observatory with the world's largest telescope, Hubble was trying to settle a debate about the nature of spiral nebulae. Were these fuzzy objects part of our Milky Way galaxy, or were they separate galaxies at vast distances?
His measurements proved they were separate galaxies, but that wasn't the revolutionary discovery. Using Cepheid variable stars as distance indicators, Hubble calculated that these spiral galaxies lay millions of light-years away, far beyond the boundaries of the Milky Way. But as he plotted galaxy distances against their velocities, Hubble noticed an impossible pattern. Every galaxy was moving away from us, not just a few galaxies, not just distant galaxies. Every galaxy he could measure showed red-shifted light, indicating motion away from the Milky Way. This seemed to place Earth at the center of a cosmic explosion. More disturbing still, the farther away a galaxy was, the faster it seemed to be receding. Galaxies twice as distant moved twice as fast. Galaxies 3 times farther moved 3 times faster. This relationship, now called Hubble's law, suggested a direct proportionality between distance and recession velocity. Hubble initially interpreted this pattern as evidence for motion through space. He imagined galaxies racing away from us through a static cosmic arena, like debris from an explosion expanding into empty space. But this interpretation created impossible problems. If all galaxies were moving away from us, it would mean we occupy the special center of the universe. This violated the Copernican principle that Earth doesn't hold a privileged position in the cosmos. The resolution came from understanding that space itself was expanding. Imagine dots painted on a balloon operating in reverse, but starting to deflate. As the balloon inflates, each dot sees every other dot moving away. The farther apart 2 dots are, the faster they separate. Yet no dot is special. No dot sits at the center of expansion. This insight transformed Hubble's discovery from a measurement of galactic motion to evidence for cosmic expansion. Galaxies aren't moving through space. Space itself is stretching, carrying galaxies along like raisins in rising bread dough. Critical density. There exists a precise amount of matter that determines whether the universe will expand forever or eventually collapse back on itself. And we live quite close to this cosmic knife's edge.
This critical density equals approximately 5 hydrogen atoms per cubic meter of space. By any reasonable standard, this is almost perfectly empty. Yet this small amount of matter, scattered across enormous volumes of space, determines the ultimate fate of everything. The physics behind critical density comes from the competition between expansion and gravity. Expansion separates galaxies, spreading matter across ever-increasing volumes of space. Gravity tries to pull matter together to reverse the expansion and cause cosmic collapse. The strength of gravity depends on how much matter exists per unit volume. If the universe contains more than critical density, gravity wins. Expansion slows, stops, and reverses toward the big crunch. If the universe contains less than critical density, expansion wins. The cosmos expands forever, approaching heat death as matter spreads infinitely thin. If the universe contains exactly the critical density, expansion asymptotically approaches zero velocity, but never quite stops. This third case represents perfect balance between expansion and gravity. Multiple universes. Right now, as you read these words, trillions of other universes might be undergoing their own expansion histories from their own big bangs. These parallel universes don't exist far away in our space. They exist in completely separate spaces with no connection to ours. Each universe would have its own 3 dimensions of space, its own time dimension, and its own expansion history. The multiverse might be expanding on multiple levels simultaneously. In eternal inflation models, our observable universe represents just a tiny patch of a much larger inflated region. But inflation doesn't stop. Quantum fluctuations continuously trigger new episodes of inflation throughout the larger space, creating bubble universes that expand and evolve independently. Each bubble develops its own physics, its own constants of nature, and its own expansion dynamics. While our universe has been expanding for 13.8 billion years, other bubbles might have been expanding for trillions of years. Yet others might have just begun their expansion a few million years ago. Information and the expansion paradox. Every thought you've ever had, every memory you formed, every piece of information that makes you who you are exists as specific arrangements of matter and energy in space, and cosmic expansion is slowly stretching these arrangements toward dissolution. This creates a fundamental paradox in physics. Information cannot be destroyed, yet expansion seems to distribute information across such wide distances as to make it practically irretrievable. The paradox begins with the holographic principle. Theoretical physics suggests that all information contained within any volume of space can be encoded on the surface that bounds that volume. Like a hologram that stores 3-dimensional images on 2-dimensional surfaces, the universe might store all its information on cosmic boundaries. But expansion continuously increases the surface area of any boundary. As space grows, the amount of information that can be stored on cosmic surfaces also increases. This means the universe's information storage capacity grows over time. However, this growth creates new problems. The information that defines your consciousness exists in the specific patterns of neural connections in your brain. These patterns depend on precise arrangements of molecules, on precise arrangements of atoms, on precise positions in space. Only our local galaxy group will remain visible. Future astronomers will observe a universe that appears to contain just a few dozen galaxies, surrounded by empty space. The Milky Way, Andromeda, and their satellite galaxies will have merged into a single giant elliptical galaxy floating alone in the void. The cosmic microwave background, our clearest evidence for the Big Bang, will also disappear. Expansion will stretch this ancient radiation to wavelengths longer than the size of the observable universe itself.
future instruments will detect no trace of this primordial light. These progressive scientists might develop entirely different cosmological theories. They might conclude that their single giant galaxy has existed forever in an infinite, unchanging void. They might never imagine that their cosmos once teemed with billions of galaxies pulling away from each other due to cosmic expansion. They will inhabit a universe stripped of its own history. Let's review the Q&A section. So why is the question, where is the universe expanding to, like asking what's north of the North Pole?
When you ask, where is the universe expanding to, you're making an assumption that seems perfectly reasonable but is actually impossible. You're assuming that expansion needs a pre-existing space to expand into, like how a balloon needs air or a city needs countryside. But the universe is not like a balloon. The universe is space itself. When space expands, it doesn't grow towards something else. As it grows, it creates the very concept of something else. There's no external arena because the universe defines what external means. This isn't a limitation of human language or a failure of scientific imagination. It's a fundamental feature of reality. Before expansion, the concepts of into and outside don't exist. Expansion doesn't just create more space, it creates the logical framework that makes spatial relationships meaningful. The universe isn't expanding into something because as it expands, it creates the very concept of something. Think of it like this. Asking where the universe is expanding to is like asking what caused the first cause, or what contains the container of everything. The question assumes categories that only make sense after the thing you're asking about has already happened. The universe expands by becoming more universe, not by growing toward non-universe. This realization transforms our understanding of cosmic expansion from a mechanical process into something much deeper. Expansion isn't just the universe getting bigger, it's reality bootstrapping itself into existence. Each cubic centimeter of new space that emerges creates new possibilities for matter, energy, structure, and complexity. The universe isn't expanding towards some predetermined goal. It's expanding into the infinite potential for what can be. We're not passengers on a cosmic vehicle traveling towards some destination. We're part of the process by which reality creates itself. Our consciousness, our questions, our desperate need to understand where the universe is expanding to are all expressions of the universe coming to know itself. The expansion we observe isn't separate from us. We are expansion. We are space and time and matter and energy, organizing ourselves into patterns complex enough to ask questions about our own existence. This perspective resolves the paradox of cosmic expansion while revealing an even deeper mystery. If the universe creates its own space and time, if it serves as its own stage and audience, then what we call existence might be far stranger than any science fiction has imagined. We might be living inside a self-creating, self-sustaining process that has no beginning or end, no inside or outside, no purpose beyond the magnificent fact of its own becoming. The universe expands into itself, creating infinite room for infinite possibilities, including the possibility of beings like us, who can gaze in wonder at the entirety of this impossibly beautiful process. The question, where is the universe expanding to, led us on a journey through inflation and dark energy, multiple universes and quantum foam, the beginning and end of time itself. But the deepest answer was always hiding in plain sight. The universe expands into mystery, into wonder, into the infinite capacity for more questions, more discoveries, more moments of understanding, moments of recognizing that we're part of something far larger than ourselves, but intimately connected to our smallest thoughts.
We are the universe, asking where it's expanding to. We are expansion, asking where it's going. We are space and time, awakening to our own existence and marveling at the infinite creativity of the process that brought us into being. And in this realization, the question transforms from a puzzle to be solved into a celebration of the magnificent impossibility of existence itself. Thank you for listening to me. Until we meet again in other explorations and discussions. Merry Christmas. Good night.